All right, here we are on video number 3. We are going to start by classifying polynomials by degree and by number of terms. I'm going to zoom in just on the A, B, C, and D, and we're going to figure out for numbers 1 through 4 whether each polynomial is degree 2, 3, 4, or 5, and then for numbers 5 through 8 whether we have a binomial, polynomial, monomial, or trinomial. So let's start with letter A. We have 4x to the 4th minus 12. For degree, we are looking for the biggest exponent. And our biggest exponent on letter A is a 4. Okay. Since we have that 4, that is a 4th degree polynomial, so that is going to be number 3. Okay, then we look at how many terms we have. We have 1, 2 terms, so that is a binomial. That is number 5. Okay, so put A for 3 and 5. Let's look at B. B, we look for biggest exponent. It is a 5. 5, so 5th degree, that is number 4. And then we look for how many terms. 1, 2, 3, 4 terms. Okay. Binomial means 2. Polynomial means 4, monomial means 1, and trinomial means 3. So we're going to use the word polynomial for this since it is 4 or more terms. That is number 6. C, biggest exponent, is a 2. That is a quadratic, which is degree 2. So that should be number 1. And then we have 1, 2, 3 terms, 3 like tricycle. Okay, 3, so that is number 8. And D, biggest exponent is a 3. Okay, 3 for biggest exponent, degree 3, that is number 2. And there's only one term in this whole thing, making it a monomial, which is number 7. Okay. Next set. Number 9, we are supposed to add these polynomials. We know we're supposed to add, first off, because the instructions say add, so make sure you're reading these instructions. Second thing, in between our 2 sets of parentheses, there is a plus. Do not multiply these together. That'll take you a long time, and it's not what we're looking for. Okay, we are adding. So we are just combining like terms. To do that, we look for our biggest exponent. So let's start with a 3 exponent here, and we do have another 3 exponent there. Let's add them together. We have a 2x cubed plus an 8x cubed, that is 10x cubed. Next, look for next biggest exponent, which is a 2. So we have a negative 3x squared and a negative 5x squared. We add those together, and we get negative 8x squared. Last, we have x's to the first power and x to the first power, right? Invisible 1 exponents. We have a negative 1 plus 7. Negative 1 plus 7 is 6, so plus 6x. Okay, notice that on each of these terms, when we added together the 2 like terms, we did not change the exponents. When you're combining like terms, the answer part should be a like term with the like terms you already had. Okay, this is it. There's your answer. Number 10. We are subtracting this time. So we have treated subtracting a lot like there is a negative 1 in front of our second parentheses. So we are going to distribute that negative 1 times those other 3 terms. So that makes this a negative 10, a negative 6x cubed, and a positive 2x squared. Our first polynomial stays exactly the same because there's nothing in front of it to multiply. Okay. And now we can just combine like terms like we just did on the other problem. Biggest exponent is a 3, so we have a 6x cubed and a minus 6x cubed. Positive 6 minus 6 is 0, so those terms completely cancel each other out. There is no x cubed, they're gone. Next, x squared. So we have a 2x squared and a 3x squared. 3x squared plus 2x squared is 5x squared. Then we don't have any just x's, so we can move on to constants. Constants are the terms that do not have any x's. And this says negative 3 minus 10, which is negative 13. There's our answer. Number 11. We are supposed to multiply. All right, here's where we get to distribute. We have one term on the outside, and then we have 3 terms on the inside. 1 outside times 3 inside is 3, so we should be getting 3 terms. Okay. As we multiply, we are going to be multiplying the coefficients together, which are your big numbers, multiply together your x's, and multiply your y's. As we multiply coefficients, we just multiply like normal, but when we multiply variables, we add together exponents for the same types of letter. All right, so here we go. -3 times 5 is -15. Then we have x to the 4th times an x to the invisible 1. So we will have x's and add the exponents together. 4 plus 1 is 5. We have a y squared, and there's no more y's, so we still have y squared. Next set, -3 times -6 is +18. We have x's, we have x to the 4th and x to the invisible 1. 4 plus 1 is 5, so x to the 5th. And then y's, we have y to the 2nd and y to the 3rd. 2 plus 3 is, again, 5. Last set, -3 times -2 is -6. We have x to the 4th power with no more x's. And then we have y squared and y to the 4th. 2 plus 4 is 6. Okay, on number 12, the instructions again say multiply, and we are going to write our answer in standard form, which is biggest to smallest exponent. Since we are multiplying, we're going to be doing 2 terms times 3 terms. 2 times 3 is 6, so we should be getting 6 terms in here. All right, let's distribute. We have 3x times 4x squared is 12x cubed. 3x times -6x is -18x squared. And 3x times 11 is plus 33x. Moving to -5. -5 times 4x squared is -20x squared. -5 times -6x is plus 30x. And -5 times 11, -55. Okay, as we do each of the distributings, like what we have in red, notice that our terms in red are all not like terms. So that means that all of our exponents are going to be different. So that's a way to check your work as you're moving along. We also have in blue, not like terms, x squared, x, and then a constant. Okay, let's combine like terms now, and we're going to do it in such a way that we write the answer in standard form as we go. Okay, so this should feel a lot like number 9 when we're adding like terms. First term, 12x cubed, all by itself, no other x cubes. So write it on down. Next, x squared, so we have a -18x squared and a -20x squared. -18 minus 20 is -38. And then keep the x squared. We have 2 terms that have just x's on them. 33 plus 30 is 63. Keep the x. And the last term all by itself, that constant, is -55. Okay, and again, all of our terms are not like terms. Exponents from biggest all the way down to the smallest exponent, and our constant at the end. So that's our answer. Okay, on number 13, we are going to use a graphing calculator. You could factor this one and solve for x if you want, or you can just plug it into your graphing calculator. You would plug into the y equals the x squared minus x minus 12, making sure you're using the minus key, not the negative key. When you do that, we should be getting either a graph, or you can look at the table. It's your choice. Our graph would look something like this, where we have a parabola that crosses over the x-axis at -3 and 4. And if you are at a normal zoom setting, you should be able to just count those individual little tick marks. Okay. If you'd rather, instead of looking at the graph, look at a table, you're going to hit second graph and then look at your table. We've got some x and y values. We'll be looking for where the y value equals 0. And number 13 here does have 2 points where our y value is 0. And they happen where x is -3 and where x is 4. So the question, what are the zeros, is looking for what are the 2 x values where the y value is 0. And we can tell from both the graph and from the table that negative 3 and 4 are the two x values that make that happen. Okay, when we learned about radical form to exponential form and exponential form to radical form, we talked about the power and the root. The power, like in the sun, is up above. So power is on top of a fraction exponent, and the root is below the ground. So when we take a look at number 15, the power must be the 5, and the root must be the 4. Okay. How that appears on number 14 is the root is the 3, like it's in the radical, and the 8 is the power. Okay, so we're going to be swapping these two forms with each other. So 14, we're going to keep the x that is inside of the radical, and we're going to give that x an exponent. We said 8 was the power. Power goes on top like the sun, and the root is the 3. 3 goes underneath the ground, so it's the bottom of the fraction, and that's our answer. So this one should be really quick. Number 15, we have 8y. It is inside the parentheses, so it is going to go inside or underneath the radical. It doesn't matter if you put parentheses with the 8y or not, as long as the 8 and the y are both inside. Okay, now we're doing this backwards. We said that 5 was the power, so we're going to put parentheses around the whole thing and give it a power of 5. And then 4 is our root. The root goes with the radical, and it goes in that little nook. And that's our answer. Number 16, combining like radicals. This should feel a whole lot like combining like terms. Okay, like radicals means that the inside of the radical has to be the exact same number, and the index or the root number has to be the same. Okay. On every single one of these, the root number is the invisible 2. I'm going to zoom in on there. We have an invisible 2 root on every single one of these. Okay, you do not have to write those 2's in. Sometimes they're helpful. Okay, we can tell that both the first term and the last term are alike because the radical itself has the little root number of 2, or the index of 2, and then the inside number is a 6. Okay, so we have 5 times the square root of 6, and we have negative 7 times the square root of 6. Just like if this were 5x minus 7x, we would get negative 2x. Notice the x's don't change, right? The exponents don't change, the letter stays the same, but the 5 minus 7 is what gets us that negative 2. So the 5 root 6 minus 7 root 6 ends up being negative 2 root 6. And if you want to write that tiny little 2 in there for the index, you are more than welcome to write it in there. There it goes. Now you might notice that that little 8 times the square root of 3 has nothing to combine with it. There's no like term. So it's kind of like having x's and y's in the same problem. They're just not like terms. You cannot combine them. So this is plus 8 times the square root of 3. And if you want that little 2 in there, go for it. Okay, number 17, we are simplifying the radical. There's several important things that you need to notice on this. First off, the root number is a 3. That means we're going to be looking for groups of 3 of the same number. The next thing is the number 108. We're going to take that number 108 and we are going to make a chart for it. We want any number that you can divide 108 by. You can divide this by 2 because it's an even number. You could divide by 3 because it's divisible by 3. Or if you notice that larger numbers go into 108, you're more than welcome to divide by something else. So 108 divided by 9 is 12. Okay, so we're done with the 108. It's been broken down. Let's break down 9. 9 is 3 times 3, so we have broken down the 9. 12, 4 times 3. So 12 is done. And then 4 is 2 times 2. So 4 is done. It's been broken down. The numbers 2 and 3 cannot get broken down because they are all prime numbers. All right, so let's rewrite our radical. We had a 3 as the index, that root number. But then 108 is the same thing as 2 times 2 times 3 times 3 times 3. Okay, I always double check at this point, 2 times 2 times 3 times 3 times 3 in my calculator. actually does equal 108. Very important, because if you miss a 3 or put an extra 2 or something, it messes up your whole problem. Okay. We talked about how that number 3 was our index, the important number. Okay, so that 3 means that we need 3 of the same number. So I don't care if they're 2s, 3s, 7s, whatever. We need 3 of the same number. So I'm going to underline the 3 3s. Okay. We underlined 3s one time, so we are going to write 1 3 on the outside for that. Okay. Then the 3 for the index stays in there, and we still had 2 2s that were left over inside. We could not make a group of 3 2s because there are only 2 2s. Okay. The last thing we do is we simplify as much as possible. There's just a 3 outside, but if there was something else out there, like a 7 or something, we would do like 7 times 3. Inside we have 2 times 2, which is 4. So it's just cleaning it up, making it look a little bit nicer.